So concerning this assignment, I want us to go over again. The conventional method for separating ethyl alcohol from an alcohol water mixture is distillation. However, this procedure can at best only give a product of 95% weight of the alcohol because water and alcohol form a constant boiling mixture called an azeotrope of that composition. Simple distillation cannot eliminate the azeotrope. Instead, if a pure alcohol product is desired, benzene is added to the feed solution. Suppose it is desired to produce 1000 kg per hour of pure ethyl alcohol in this manner by distilling a feed mixture containing 60% with water and 40% with alcohol. If the distillate composition is 75% benzene and 24% water with the rest alcohol, how much benzene must be fed to the column? Now, from the question, realize that the ethyl alcohol we are talking about here is the same as this alcohol water mixture here. So it's not like the ethyl alcohol and then the alcohol here are two different things. They are the same. So because ethyl alcohol is just an alcohol compound. Now we first have to draw our diagram first before we can start with our degree of freedom. Then we go to work. Now with the question, you realize but then we can't achieve a 8%. But then if you want to achieve a pure alcohol stream from the water, then you need to add a benzene to the feed solution before you can achieve a pure alcohol. And the question is saying that when you add the benzene to the feed and then you do your separation, you are going to produce 1000 kg per hour of your pure alcohol. So we first need our process unit here, which is our separator. And then our feed is a alcohol and then water mixture. And then they gave the composition for the feed mixture. It contains 60 by weight percent of water and then 40 by weight percent of alcohol. Now the question goes ahead to say that if the distillate composition is 75% benzene and 24% water, with the rest being alcohol, how much benzene must be fed to it? And then because if you don't know the flow rate of the feed, we are using an unknown variable here as F for the flow rate of the feed, which is entering the separator, and then 40% alcohol. And that mass fraction gives us 0.6 and then 0.4. And these are distillates. The composition of the 4% water and then the rest being alcohol. So in terms of mass fractions, you'll be getting, calling the fluid of benzene as X here. And because you are feeding in a pure benzene, the mass. Now, when you feed in the benzene, according to the question, we can be able to produce pure alcohol or pure ethyl alcohol. So this bottom stream becomes pure ethyl alcohol. And then the question gave the fluid as 1000 kg per hour, which will have a mass percent of 100% or mass fraction of 1. So this is the diagram for the question. Now, after achieving the diagram, then you go straight to your degree of freedom analysis to see if the question is or not. So it's our degree of freedom. We know the degree of freedom to be number of unknown variables minus number of independent equations. So I was saying that from the question, realize that you are supposed to separate alcohol. But then when you separate, you are achieving 95% alcohol. But then you want to achieve a pure alcohol. But then before you can achieve this pure alcohol, you need to feed in a certain amount of benzene before you can achieve that pure alcohol. So we are supposed to find the flow rate of benzene that we need to achieve 100% alcohol from the mixture. So this is our separator or our process unit. We put in our feed line. So this is our feed. And then because we don't know the flow rate of the feed, we are representing that as F. Then our feed has the composition of 60%, which is mass percent of water, and then 40% alcohol. So in terms of mass fraction, 0.6 water and then 0.4 alcohol. I'm representing W as water and then A as alcohol. Now the question spoke about distillate, right? And even when we are distilling, I said yesterday that you are going to get two outputs, your distillate and then your bottoms. We don't know the fluid of the distillate, so I'm representing that as D. And then from the composition, the question gave us 75% benzene, 24% water, and then the rest being alcohol. So in terms of mass fractions, I'm going to get 0.75, 0.24, and then 0.01. And then with the bottoms, before that, from the question, it says that before you can achieve a pure alcohol, you need to put in a benzene, right? So these are benzene being fed into the separator also. And then because you don't know the fluid of the benzene, I'm using X as the fluid of benzene. And because you are feeding in a pure benzene, the mass percent is 100%, and hence the mass fraction will be 1. That's why here it's 1. This is for the benzene. The moment you feed in the benzene, then we can get a pure ethyl alcohol or a pure alcohol. And that is this, the bottoms. The question gave the fluid to be 1000 kilogram per hour. And then the composition will just be 100% A because it's pure alcohol. So the mass fraction is also 1. So this is the diagram for the question. The moment you are done with your diagram, you have to go straight to do your degree of freedom analysis to see if the question is solvable or not. So we do our degree of freedom analysis. Now, degree of freedom is number of unknowns minus number of independent equations. So from here, how many unknowns do we have? X1, F2, and then D is here, 3. So we have 3 unknowns. And the number of equations can be gotten from the component balance or the number of components present. So the components present are A, alcohol, B, water, and then benzene. When you subtract them, you get 0 as your degree of freedom. Now, the question gave an information here. However, this procedure can at best only give a product of 95% by weight of the, right? But then realize that this information generic statement given that the maximum purity you can get is 95% alcohol. But then when you put in benzene, you can get 100% of the alcohol. So this information becomes irrelevant. That's why you didn't count it as part of the number of independent equations. Now that we have our degree of freedom to be 0, then it means that we can go ahead to solve the question, and the question is solvable. You first have to start with your overall mass balance, and then your overall mass balance will be your input equals your output. So F plus X should be equal to D plus 1000. So this is our overall mass balance. You are looking at the total input and then the total output, the flow rate.
Okay, so this is what he's saying. Okay, you have your process, and what we are doing is that we have a mixture coming in. That's water and then some alcohol, and we have their compositions. So we have the water to be 60%, and then the alcohol is 40%. But then what we are saying now is that we want to get a pure alcohol stream. We can't do that unless we add another feed stream, and that's benzene. So we have the benzene being added here. So that's this stream over here. And then we have a distillate and we have a bottom. So we've been given the composition of the distillate. So we have 75% benzene, 24% water, and then 1% alcohol. And then we have the bottom stream. That's going to be just pure alcohol. So that's 100% alcohol. And we're given the flow rate in the question as 1000 kilograms per hour. So what we do is that we first start with the degree of freedom analysis. For that one, we have to get the number of unknowns and then the number of independent equations we have. We said that for the number of unknowns, if we look at our process, we don't know the flow rate of the feed stream. We don't know the flow rate of the benzene stream. And we don't know the flow rate of the distillate stream. So those become 3 unknowns. Then for the number of equations, we can get it by counting the number of components we have. So we have water, we have alcohol, we have benzene. So that will give us three independent equations. So 3 minus 3 is 0. So it means that we can solve the particular problem. Now, the other thing to notice that we have to perform a balance around the units. So we have our units here. And for that unit, we have the overall balance. So the overall balance is just looking at the flow rate of all the streams. So I have the flow rate of the feed, I have the flow rate of the benzene stream, I have the flow rate of the distillate, and I have the flow rate of the alcohol stream at the bottom. So if we should do the overall balance, we take the sum of the flow rates coming in, the sum of the flow rates of the streams that are coming in. So we have F and X coming into the unit. So those would be the input streams. It should be equal to what is coming out. Because remember, we said that when we have a continuous process, um, we are not going to have any kind of accumulation, especially when it's at steady state. So input is equal to output. And because we don't have any reaction, there's no generation, there's no consumption. So it's just input is equal to output. So we have our feed coming in, that's the F, and then the X. And then we have the distillate and then the bottom coming out. So the sum of what is coming in is equal to the sum of what is coming out. So that's what we are seeing. So if we look at the first equation down here, we have here F plus X is equal to D plus the 1,000. So the F and the X are what are coming in. And then the D and the 1,000 are what are coming out. Now he was asking about the component balance. The component balance is considering the individual components in the streams. So what we did in equation one is we found the flow rates, we work based on the flow rates of the whole stream. But now we want to do it for maybe just water, just alcohol, just benzene. So if we should do that, if we are considering just benzene, realize that the flow rate of benzene in maybe the distillate stream up here is 75%. That means that 75% of the total flow rate here is for benzene. So whatever flow rate I have here, I'll multiply it by 0.75 to get the flow rate of benzene.
Because you are feeding a pure benzene,
Yeah.
and then there's no benzene in this but then there's no benzene in the bottoms. Yes, so in this case, it means that the outer flow rate of the distillate up there is greater than the flow rate of the benzene alone. Right? So when you find it as a percentage of the flow rate of the distillate, it's just 75% of it.
What we're saying was that you look for the flow rates of the individual components in all the streams. So if we consider benzene, let's look at all the streams that have benzene. So stream X has benzene, stream D has benzene. And we know that if we want to find the flow rate of the components, it's the same as multiplying the mass fraction by the flow rate of the whole. So if I multiply the mass fraction here, which is 1 by X, I'll get the flow rate of benzene in that stream. If I multiply the 0.75 by D, I'll get the flow rate of benzene in that stream. And the input is equal to the output. So that's what we have in equation 2. So we have X is equal to 0.75D. Then we'll do the same thing for water. So all the streams that have water, stream F has water. So I'll multiply it by the mass fraction of water in that stream. So 0.6 times F, that's going to be the input. It should be equal to 0.24 times D, because that's going to be the output. Then we can do the same thing for alcohol. So we have alcohol in the feed stream, so that's 0.4 times F. And then in the distillate, it is 0.01 times D. And then for the last stream, that's the bottom stream, it's 100%. So we can just say it is 1 times the 1,000. So that's just going to be 1,000 kilogram per hour, right? So for the components balance for alcohol, it's going to be 0.4 times F equal to 0.01 times D plus 1,000. So what I was saying for water was that, sorry, for alcohol, is that we have 0.4 times F is equal to 0.01 times D, then plus the 1,000 we have here, right? If we should change the 100% here to fraction, to the mass fraction, it's going to be 1. So I can just say it is 1 times the 1,000. So that's going to be the value I'll get for alcohol, right? So that will be for the alcohol balance. But remember, we said that when we are solving these questions, we can have dependent equations and independent equations. Now, the reason why we don't need to include that, you can write out the balance for the alcohol, but the reason why we are not going to use that is because we need just three equations to solve the question, right? Three equations are going to be independent. So if I should have added the components balance for alcohol, realize that I can sum all the balances for the individual components and it will give me the overall balance. Remember, we said the last time that if we have a case like that, then it means that there's one equation that is not independent. We only want to work with independent equations. So instead of working with four equations, we work with just three equations. So any of the three equations you choose will always give you an answer. So we have equation one, we have equation two, we have equation three. We can solve them and then we'll get our final answers. So we'd ask you to try this later on, right? The rest of it is just algebra. So making this the subject, putting this equation into this equation, solving simultaneously. So what we are saying for water is that we want to look at all the streams that contain water. So if I look at stream F, there's some amount of water in that stream. If I look at stream D, there's some amount of water in that stream. So if I multiply the fraction of water by the flow rate of the entire stream, it will give me the mass flow of water in that stream. So 0.6 times F, right, should be equal to 0.24 times D. Yeah, so if we do that, we can simplify it and get this equation down here, equation 3. So 0.6 times F is equal to 0.24 times D. Then I can divide through by 0.6 to get F is equal to 0.4D. I hope it makes sense now. Saying was that if I look at this feed stream, right, I have 0.4 as the mass fraction of alcohol in that stream. So it's the same thing we've been doing. I multiply the mass fraction by the mass flow of that stream. So 0.4 times F, it should be equal to 0.01 times D, then plus the 1000 down here, because this is pure alcohol. If I had made the 100% a mass fraction, it would have been 1. So I would have 1 times the 1000. So that would be a component balance for alcohol. So the next thing is we have splitters or dividers. So we are looking at a few other units that we'll be working with, right? And these are very important as well. When we talk about a splitter or a divider, it's a unit that is going to, as the name implies, split a stream into a number of streams. So the thing about this is that if I split a stream, please note that the composition of the stream will not change. So let's say, for example, I have a bottle. It contains some amount of water, it contains some amount of salt, and I decide to pour some of it out into another container. You realize that the composition in that container wouldn't change. It's still going to be the same composition. So if I should split a stream, the composition doesn't change. To split a stream, the composition wouldn't change. So what it means is that F1, for example, might have a certain composition. F2 and F3 would have the same composition. The same thing here. So sometimes we can draw it this way or we can draw it that way. Another thing to notice is that the sum of the flow rates of the streams that were splitted will be equal to, or let's say the sum of the split streams, right, will be equal to the flow rate of the main stream it was coming from. So what I mean by that is F2 plus F3 should be equal to F1. It's a little bit like Kirchhoff's rule from what we did in, I think he has applied electricity, right? So F2 plus F3 should be equal to, the next thing we have, okay, we have an example here. So let's try this out. So it says that consider a flow splitter, sorry, which divides a stream, this is, which divides a stream containing malt, hops, and water into three branches. So the stream contains these three things: malt, hops, and water, right? Okay. It contains malt, hops, and water. Now the composition in mass percent of the input stream is given. So that's 20% malt, 10% hops, and the rest water, which means it's 70% for water, right? So that's the composition of the feed. It's going to be the same composition for all the streams. So F1's composition is going to be the same composition for F2, F3, and F4. Now the question says that further, the branch flows are regulated so that F2 is equal to 2F3. F3 is equal to 1/3 F4. Okay. And now we have F1 to be equal to 1000 kilograms per hour. So what are the flow rates in each of the branches? So what we do is that I know the flow rate of the feed is 1000 and it's splitting into three streams. If I should add the flow rates of the three streams, it should give me the flow rates of the feed stream. So F2 plus F3 plus F4 should give me F1, which is 1000. Now we have certain relations here. So if I say F2 plus F3 plus F4 is equal to 1000, I can now equate F3 to F4 with this relation here. And I can relate F2 to F3 with this relation as well. So if we should look at that, we have F1 is equal to F2 plus F3 plus F4. And we know that F2 is equal to 2F3 and F3 is 1/3 F4. So I can just substitute them in there. So I can change this F2 to 2F3. And then that F3, I'll change it to 1/3 F4. Then I would also have 1/3 F4 coming in for this F3 here, then plus F4 itself. And I already know my value for F1 is 1000. So if I should put this in, factorize F4 out, and then simplify, I can find the flow rate of F4 to be 500 kilogram per hour, right? And I can put it back in the relations we had. So we know that F3 is 1/3 F4. So I'll just find 1/3 of this value to get my flow rate for F3. Then 2 times F3 will give me F2. So I'll just multiply that answer by 2. So when I do that, I will get these answers here. And as for the composition, it's going to be the same composition. So the other part of the question said, what are the compositions of malt, hops, and water in the three branches? So it's going to be the same composition at the end of the day. Because we said that when we are dealing with splitters and dividers, the composition doesn't change. So what we are saying is that if we have a splitter, we have maybe one stream, and then we can branch it into a number of streams. But then the idea is that the flow rate of all the branches, if we add them, it should give us the flow rate of the main stream. The flow rate of all the branches, if we should add them, should give us the flow rate of the feed. Okay. Now, we know the flow rate of the feed to be 1000 kilograms per hour. And we've been given relations for F2 and for F3. We have F1 and it branches into three streams. So F2, F3, and then F4. But when we sum the flow rates of the branches, it should give us the flow rate of the main stream. So if I add F2, F3, and F4, it should give me the value for F1, which from the question is 1000. So that's the first thing to take note of. The second thing is that we've been given relations for F2 and F3. So I know that F2 plus F3 plus F4 should be equal to F1. So we can see that here. And we know that F2 is equal to 2F3 from the relation that was given in the question. And F3 is also 1/3 F4. So for this main equation up here, I can replace F2 with 2F3. And then that's F3. I can replace it with 1/3 F4. Then the F3 in the question, I can also replace it with 1/3 F4. So when I do that, I'll have this relation now. Now all I have is F1 and F4. But I know the value of F1 to be 1000. So if I should simplify, I would have here 1000 to be equal to 2/3 F4 plus 1/3 F4 plus F4. So if I should add everything at the right hand side, it will give me just 2F4. So I can make it 1000 over 2, right? So 1000 is equal to 2F4. So 1000 over 2 will give me the value for F4, which is 500 kilograms per hour. But you also realize from the question that F3, we said is 1/3 F4. So if I should find 1/3 of the 500, it will give me the flow rates for F3. So that's the 166.67. And then we are also told that F2 is 2 times of F3. So once I find the flow rate for F3, the 166.7, I can multiply it by 2 to get the flow rates for F2. Okay. The last part of the question is, what are the compositions of malt, hops, and water in the three branches? So we realize that for splitters and dividers, we said the composition does not change. So whatever composition we're given in the question is going to be the same composition for the other streams. So it was 20% for malt, 10% for hops, and then the rest was water. It's going to be the same composition for the other streams. So we are looking at mixers now. So unlike splitters, for mixers, the compositions will change. That's one thing to note. Right? The only time the composition doesn't change is if what we are mixing has the same composition. So I'll explain that a little bit further. So we have here F2 and F3. If they had the same composition and I mix them, the composition is not going to change. So let's say F2 was 30% salt, 70% water. F3 is also 30% salt, 70% water. When I mix them up to get F1, it is still going to be 30% salt, 70% water, especially if they have the same mass flow. So if they are the same stream and I'm mixing them, the composition doesn't change. But if they have different compositions, then the composition can change. Okay. Now, for mixers, it's the reverse of the splitters. So instead of splitting a stream into a number of streams, we are joining a number of streams together. But it works with the same principle. So everything that is coming in, if we sum it, should be equal to the stream that is coming out. So F2 plus F3 should be equal to F1. Now we can look at systems involving multiple units. So everything we've done so far, looking at just one unit. Maybe you have one distillation column and you have one distillation column and then you have maybe the top stream, the bottom stream, the feed stream. But now we want to look at a case where we have more than one unit. Maybe we have a distillation column, we have maybe a mixer in there, we have a splitter in there, we have a number of units all coming together. So this part is also very important. It applies the same principles. But this time, instead of doing it for just one unit, you can do it for a number of units together, right? And the thing about this is we are going to look at two important things, what we call a recycle and what we call a bypass. Okay, so we'll look at how to perform calculations based on those as well. So this is an example of what we are talking about. We have one unit and we have another unit. So we have unit A and unit B. Now, if you look at the darker blue circle, right, it is just doing the balance around unit A. So the inlet to A and then the outlet from A. So that's stream 1, stream 2, and stream 3. So we can do our material balance on just those streams. So if you look at this, unit A, balances can be written on streams 1, 2, and 3. If you look at the lighter blue circle, it is just considering unit B. So we can look at the feed to unit B, which is stream 3, and then the outlet. So that is stream 4 and stream 5. So here we see that unit B balances can be written on streams 3, 4, and 5. And we can also do an overall balance. So for both units. So I'm going to look at the feed coming in overall and then all the outlets overall. So that's the red circle we have here. So the feed coming into both units, all the feed streams we have, right? It's just stream 1. And then the outlets we have will be stream 2, stream 4, and stream 5. Now, one thing to note is that streams that are coming from a unit and entering another unit are not considered when we are doing an overall balance. So what I mean by that is we can see stream 3 leaving unit A and entering unit B. If I'm doing the overall balance, I'm not going to include it because it is not acting as a feed to the overall system or an outlet from the overall system. It's more like an intermediary stream. So what we are saying is that we can have more than one unit. We have unit A, we have unit B. Part of unit A is going to unit B. So if I want to do the balance for just unit A, I will consider the feed to unit A and then the outlet from unit A. So that's where the darker blue circle is. So that's stream 1, stream 2, and stream 3. Then if I want to do for just unit B, that's where the lighter blue circle is. So I'll have stream 3, which is the feed to the unit, stream 4, and stream 5. And I can also do the overall. So if I'm doing the overall, I'm going to consider all the feeds and all the outlets. But I'm not going to include the ones that are joining the units to each other. So something that is coming from unit A to unit B will not be considered. So in that case, it's just going to be stream 1, stream 2, stream 4, and stream 5. So I think we already spoke about this. So for unit A, we are doing the balance on stream 1, 2, and 3. For unit B, we are doing the balance on these ones. So yes, and you realize that we are having three units. Okay, so let's say we have S number of components, right? That will give us S independent equations. So maybe let's say our S is 2. We have just 2 components, so maybe water and alcohol. So we're going to have 2 equations, right? Or just like with the previous example we did, we had here water, alcohol, and benzene. So that was 3 components. So that's what we are just trying to look at here. So let's say our S here was 2 or our S was 3. That's the number of components we have, right? Coming from unit A, number of components we have around unit B, and even for the overall thing. So realize that we have 3 independent equations, right? So if we look at it carefully, we can have 3 independent equations for just unit A, 3 independent equations for just unit B, and then 3 independent equations for the overall. So the number of equations that we'll get at the end of the day, right, will be 3. That's the number of units times the number of components. So what we are saying is that if I should do the balance around unit A, if we should have maybe the balance around unit A, if we should take unit A, right, and maybe we have 2 components, maybe once again salt and then water, it means that we can get 2 equations that we would use for unit A. Then the same salt and water would give us 2 equations for unit B. And then the same salt and water will give us 2 equations for the overall. So the number of equations that we can get will be based on the number of units plus the overall times the number of components. So here we have 2 units, unit A and B. And then if we include the overall, we would have maybe 3 things we are looking at. And since we are working with 2 components, we can get 2 equations for each of those 3 cases. So that becomes the 3 times the 2. I hope it makes sense. But then the number of equations that would actually need to work with would just be 2 sets. Because realize that if I should find the balance around unit A and the balance around unit B and sum them, it will give me the balance for the overall system. So in that case, there's a set of balances that are not independent. So we have an example here. A separation train consisting of 2 distillation columns designed to separate a mixture of benzene, toluene, and xylene into 3 streams, each rich in one of the species is shown below. So we have a system here. We want to separate the feed into 3 streams, and we want the 3 streams to be rich in one particular component. Right, okay. So given a feed rate of 1000 moles per hour of a mixture, so that's going to be our N1. That's the feed, 1000 moles per hour. And the composition, we have 20% of benzene in that stream, 30% of toluene, and the rest. So that's going to be 50% for xylene. And we'll be told that is more percent. Then we have the bottom's product of 2.5B and 3.5 for toluene. Sorry, 35% for toluene. and that's obtained in the first unit. So for the first unit, the bottom's product, they give us the composition for benzene, for toluene, and then for xylene. Then we're also given the overhead products for the second unit. So for the second unit, that's unit B. We're given the composition of benzene, toluene, and xylene. I hope you get what we are talking about. So if you look at it critically, we've been given the flow rates for the feed. We've been given the composition for the bottom. We've been given the composition for the top. So if we are having a system like this, we can do the balance over each unit. Then we can do the overall balance as well. So if I'm looking at just unit A, so there's supposed to be Y here, and then there's supposed to be B here. There's some amount of xylene here and some amount of benzene.
With this particular question, the diagram is part of the question. So they didn't see how they link
Okay,
the buttons in the unit A to the unit B.
okay,
But then
okay.
if it was a question on its own, you see something like the buttons from the first unit is being sent to a second unit, and then you know which of them is being sent to the second unit, whether the distillate or the buttons. Per this question, the diagram is part of the question. So the question didn't really talk about which of the buttons, which of the streams from the first unit was actually sent to the second unit. The diagram was part of the question already. So the question didn't have to talk about whether the buttons from the first unit was sent to the second unit. But then in the case where the diagram wouldn't be part of the question, then to be part of the question that the bottom from the first unit is being sent to the second unit for further separation. Then in your diagram, you know how to connect your bottom to the second unit.
We have a case where we are trying to separate three components, and we want to use two streams based on the question. So the question is telling us that we have unit A and we have unit B. And from the diagram, we see the bottom stream of unit A going into unit B. The question gives us the value of N1. That's the 1000 mole per hour here. And it gave us the composition of that stream. So 20% B, 30% T, and then the rest for xylene. So that's going to be the composition of the feed. And the question also gave us the composition of the bottom's products from the first unit. We said that a bottom product of 2.5 B and 35% C is obtained in the first unit. So for the first unit, the bottom product, they give us the composition. And the question also said that an overhead product of 8% B and 72% T in the second unit. So for the second unit, they give us the overhead product composition. They give us the composition of this part here, the overhead product. So what we can do is that we can find the balance around the individual units, and then we can find the overall balance as well, right? So if you are looking at the um for let's say unit A, the component balance, look at, okay, I think, yes, let's start with this one. So let's look at equation 4 here. We have the mass, sorry, it's mole, the mole fraction of B, of benzene in that stream multiplied by the mole flow of that stream being equal to the mole fraction of benzene in stream N2 multiplied by the mole flow of that stream, then plus the mole fraction of benzene in N3 multiplied by the mole flow of that stream. So it's just like what we did earlier over here, where we had 0.6 F being equal to 0.24 D. It's the exact same thing we are doing right now. So we are taking the mole fraction of the stream and multiplying it by the mole flow of that stream. So the way the notation is, the superscript, right, is talking about the components. So if it is B, it's for benzene. If it is T, it's for toluene. If it's Y, it's for xylene. And then the subscript is talking about the stream number. So if it is 1, then it is stream N1. If it is 2, it is stream N2. If it is 3, it is stream N3. So what we see in equation 4 is that the mole fraction of benzene in stream 1 times the mole flow of stream 1, that's the feed, is equal to the mole fraction of benzene in stream N2
times the mole flow of stream N2 plus the mole fraction of benzene in stream N3 times the mole flow in stream N3. Then we do the same thing for toluene and then the same thing for xylene. Then when we look at unit B as well, now our feed is N3. So I'll find the mole flow of benzene in stream N3 multiply, maybe I'll find it by multiplying the mole fraction by the total mole flow. And that should be equal to the mole flow of benzene in stream N4 times the mole fraction times the total mole flow. Degree of freedom analysis for the overall system. But the thing about the degree of freedom analysis is that you can do it for each unit, even before you start writing your balances. You can do it for each unit, and you can do it for the overall system. But then remember, the degree of freedom analysis allows you to know whether your system can easily be solved. So there's a case where maybe you do your degree of freedom analysis for unit A and it is not solvable. You do it for B and it is solvable. So you start by solving unit B. So it gives you an idea of where you can start solving your question from. And doing it for the overall is also quite similar. It's still your number of unknowns minus your number of independent equations. So the question gave us some compositions and it gave us a diagram. So the question gave us the composition of N1 as 1000 mole per hour, right? And it gave us the composition of the bottom stream from unit A and then the top stream from unit B. But then what we want to look at for now is how to write the balances for each of the units and then for the overall system. So what I was saying was that with the notation that we are using here, if you see a superscript, it's talking about the components. So B is for benzene, T is for toluene, and Y is being used for xylene. But then when you look at the subscript, it's talking about the stream number. So if I see 1 down here, it's talking about stream N1. If I see 2, it's talking about stream N2. If I see 3, it's talking about stream N3. Then what we are also saying is that if I want to find the mole flow of a particular stream, of a component in a particular stream, it will be the mole fraction of the component multiplied by the mole flow of the entire stream. So if I want to find the mole flow of just benzene in stream N1, it's going to be the mole fraction of benzene in stream N1. That's XB1 times the mole flow of that stream. That's N1. Remember we said that input should be equal to output. So I also look for the outputs for unit A. So the mole flow of benzene coming out in stream N2 will be the mole fraction of benzene in that stream. That's X2B multiplied by the mole flow of that stream. That's N2. So we can do this for unit A and for unit B. It's the same thing we've done so far. But now let's look at it for the overall system. Remember for the overall, we said we are going to consider N1, N5, N4, and N2. We're not going to consider what is coming from N3. We're not going to consider what is coming from unit A and going to unit B. So you're looking at the overall feed and the overall outlets, right? So it means that I'm going to do my balance considering N1 as my feed stream, and then N2, N4, and N5 as my outlet streams. So for the overall balance, if maybe I'm doing it for, let's do for toluene because that one is longer. That's equation 2. I'll have the mole fraction of toluene in the stream N1 multiplied by the mole flow of that stream. That should be equal to, now we are considering N2, the mole fraction of toluene in stream N2 multiplied by the total mole flow of that stream. Then we also have toluene in N4 as an outlet. So the mole fraction of toluene in that stream multiplied by the mole flow of that stream. Then we have it in N5 as well. So the mole fraction of toluene in that stream multiplied by the total stream. Looking at recycle streams now. When we talk about a recycle, it means that we are just taking a stream that is further down in the process and feeding it back into something that was before, right? So what I mean by further down in the process is, if you look at this example we had here, realize that unit B follows unit A. Something comes from unit A to unit B. So unit B is further down the process. So if I should take a stream from unit B and send it back somewhere in unit A, then I'm doing what is called a recycle. So I take a stream and I feed it into an earlier part of the process, right? And there are a number of reasons why we do this. So we have some examples here. Maybe we want to increase the conversion of a reactant when we are dealing with reactors, or we want to recover some materials, or we want to make a stream more dilute. So these are some reasons why we do recycling. And we also have bypass. So it's the opposite of recycle. So whereas the recycle, you are feeding it backward. For the bypass, you are going to feed it forward into a stage you've not yet got into. So let's assume we had, I think, let me see, there's an example. Okay, so there's an example here. So here we have our process unit here, and we have a splitter afterwards, something that is coming after the unit. So it splits the streams into two, and it sends one of the streams back to join the feed stream. So this is a recycle. So I'm taking something that is later down the process, and I'm sending it back to an earlier part of the process. For bypass, or which is also called cutback, I'm rather taking something from an earlier part of the process and feeding it to a later part of the process. So I'm going to skip some units and then feed it to another part of the process. And please take note of something. When you are dealing with recycles and bypasses, you would have splitters and mixers coming in there. So you can also do a balance around the splitters and then the mixers. The reason why I'm saying this is because you might have a question and you do your degree of freedom analysis of maybe unit A, and then for units B, and then for the overall, and you realize that none of them can be solved. But then when you do it for maybe the mixer or maybe the splitter, you will get a starting point you can work with. So the mixers and then the splitters are also units that you need to consider, right? Okay. Sometimes you won't see them draw a unit like you see here, the pink and the blue circles. Sometimes it will look like something like this. So you can see that the stream is just being broken into two. The stream was coming from here and it was broken into two. It implies that there's a splitter here. And we can also see that there's a stream coming in this way. And then I'm adding another stream to it. So it implies that there's a mixer here. Okay. Now, when we're talking about the page, what we are saying is that, yes, I might split the stream to recycle some of it, but I'm also going to release an amount of it. Do you get it? So I have a splitter here. It splits the stream into two. So this part here might continue with the rest of the process. But this part here, I further split it again. So I might have some parts being recycled and some parts I'm just maybe releasing to the environment. Do we get it? So a purge is more like in quotes an unwanted stream. Let me put it that way. So we have an example. You have a stream and that contains maybe some nitrogen, some oxygen, and some other materials. But you don't want to send everything back to the process. You don't want to recycle everything. And you also don't want to send everything further to another unit. So what you can do is that you can release some amounts of it. So that's what the page is talking about. Okay, sure. So for an example, we have fresh air containing 4 more percent water vapor is to be cooled and dehumidified to a water content of 1.7 mole percent water. Sorry. A stream of fresh air is combined with a recycled stream of previously dehumidified air and passed through the cooler. So let's take it one by one. So we have the units here. So we have our units here. Sorry, that's the air conditioning units here. What we are saying is that we have a feed coming in, and that's 4% more percent of water vapor. So it's going to be 4 divided by 100. That's 0.04. That's going to be the mole fraction of water in that stream, right? But then it is fresh air and it's containing water vapor. It means that the balance is going to be dry air. So it is dry air plus some amount of water vapor. That's what gives us the um, humid air. And we know the amount of water vapor in there to be 4 mole percent. So it means that the amount of dry air in there is going to be 96 mole percent. So that's what we have. We have 4 um, percent for water. And then if we look here, we have 96 for the dry air. Now we are being told that we want to get air. We want to dehumidify. So we want to remove some water. And when we remove the water, we want the outlet to contain 1.7 mole percent water. So what is going to come out to be 1.7%. So 1.7 divided by the 100, that will give us the 0.017 we see down here. And then the rest of it is going to be dry air. So that's going to be the 98.3%. That's what we see over here. Then the question goes on to say that a stream of fresh air is combined with a recycled stream of previously dehumidified air. So it means that this fresh air that is coming into the system, we are going to add a recycled stream from what we have dehumidified. So the dehumidification is just saying that we pass it through this condenser. It condenses some of the water out of the air. So the amount of water in the air reduces. But what we want to do is that we want to take some of that dehumidified air and send it back to join the feed stream, to join the fresh air stream. So we know the composition of the fresh air stream, what was coming in, and we know what we are targeting. So if I should send some back, it means I'm going to split. So if I'm going to split it, remember we said for splitters, the composition doesn't change. So realize that the composition here is the same as the composition here. We have 0.983, 0.017. After I split it, it's the same composition. 0.983 for the dry air, 0.017. And then even the stream that we are recycling, because it was part of what we split, it's also going to be 0.983, 0.017. So I can now send this back. And if I'm sending this back and I'm joining it to the fresh air stream, then it means I'm going to do mixing at this point. Remember for mixing, we said that the compositions can change. So we need to find a new composition. So when we recycle and we join it to the fresh stream, the question tells us that the blended stream entering the unit, so that's the mixture of the recycle and the fresh air stream, contains 2.3 more percent of water. So they've given us the composition of that blended. So we have that here. So we can go on with the question. The question now tells us that taking 100 moles of dehumidified air delivered to the room as a basis of calculation, we should calculate the moles of fresh food, moles of water condensed, and the moles of dehumidified air recycled. So what we are saying is that the amount of dehumidified air we are taking out at the end of the day should be 100 mole, should be 100 moles. So that's what we have here. And now we have a number of unknowns. We don't know our feed. We don't know N2. That's the flow rate of the mixed stream. We don't know N4, and we don't know N3 here. No, so this is N5. We don't know N5. We also don't know N3. Right, so we have a number of unknowns, and we have a number of components. So that will give us a number of equations, and that can inform what we will do. But the one thing to take note of is that, remember we spoke about having dependent and independent equations, right? If we're looking at the number of unknowns in particular, realize that over here, I have N1, which is, so I have N1, I have N5 and N2. It's a mixer. So if I add N1 and N5, it will give me N2. So in effect, instead of me saying I have 3 unknowns in this case, I actually have 2. Because if I know 2 of them, I can determine the third one, right? And then the same thing happens here. So if we look at it here, we have 2 variables here. That's the air and then the water. So as if we look at it for the overall system, we have the overall feed, that's N1. And then we have the overall outlet, that's N3. And then the 100 moles. So that's the larger broken line we see around the unit. That's the balance for the overall system. Is that okay? is going to be N1 to be equal to N3 plus 100. So that's what we are trying to say from there. That we have two things we don't know. So that's the N1 and then the N3, right? And then the balances that we are going to work with are going to be 2 because it's just dry air and water. So the degree of freedom there is going to be 0. So now can we realize that for a system like this, if we do the degree of freedom analysis for the overall system, we get 0. So it means we can solve the overall system first. When we do that, it will give us the value for N1 and N3. Then we can use it to further solve the smaller units within the question. So the changing composition is coming from the fact that the composition here and the composition here are different. So if I should actually find their mole flows and then use those mole flows to find the new mole fraction, it will change. But here in the question was given to us, we don't add mole fractions to get the new mole fractions. I don't add a mole fraction of the stream. So over here, it was given to us in the question. In a case where it is not given to you, it means that you would have to find it. And you find it by finding the actual mole flow. You add the mole flows. Then you will now find the total mole flow. Then you can use it to find the new mole fraction. I hope you get what I'm trying to say. So in a case where it's not given to you, you will find the mole flow of the dry air in N1, the mole flow of the dry air in N5. Then you add it to get the new mole flow of dry air. Then you divide it by the total mole flow of the two streams to get the new composition for dry air. So we don't add the mole fractions. Okay. So what we're saying was that you can do the balance for the overall system. So you have your N1 to be equal to your N3 plus your 100. Then you have two components, that's dry air and water. So you can also do a components balance. So you have two equations, you have two unknowns or two variables. Your degree of freedom is 0. You can solve it and then you can get it for both of them, right? But we can also look at the degree of freedom analysis for the other parts of the system. So if we consider the mixing points, realize that for the mixing points, that is over here. Remember I said that instead of we saying our unknowns are 3, our unknowns will be 2. The reason is that N5 and N1 can be combined to N2. So instead of saying my unknowns are N5, N1, and N2, I can just say that my unknowns are N1 and N5 because N2 is equal to N1 plus N5. Once I know those two, I will know the value for N2. So the only unknown we are considering, or the only unknowns we are considering, will be N1 and then N5. We won't consider N2 because we can get it from adding two other things. So in that case, for the mixer, just this part here, a number of unknowns will be 2. Okay, so what I was saying was that for the mixer here, a number of unknowns will be 2. And we still have two components. So it's 2, unknown variables are 2. And then the number of components are also 2. So that will give us two equations. So 2 minus 2 is still 0. So for the mixer, we can find the values around it. And if you look at the cooler itself, that's this unit over here where we have the air conditioner written here. If I look at the balance around it, the feed to it is N2 and the outlet is N4 and N3. So my overall balance is N2 should be equal to N4 plus N3. Now, if I look at this, my number of unknowns is N2 and then N3 and then N4. So the number of unknowns for that is going to be N2. It's going to be N2, N4, and then N3. And the number of components I have there are 2. So it's supposed to be the 3 minus the 2. So we can't just solve for just the air conditioner as it is. I think we'll have to check this part again because N3 is also unknown. We don't know the amount unless it was stated in the question. So what I'm saying is that for the air conditioner part, N2 is coming in, N3 and N4 are coming out. We don't know their compositions, right? But then we can say that N2 is equal to N3 plus N4. So once again, I can write N2 as N3 plus N4. And then I can have my number of components as well. That's 2. That's giving me 2 equations. So I think that's why they did it this way, right? So that you have your variables to be two, your balances to be two, and then your degree of freedom analysis, you get your DFA to be zero. Then for the parts that we are doing the splitting, we don't know N4 and we don't know N5 as well, right? So the number of variables are two, N4 and N5. But then you realize that if we are supposed to do a balance, because it's the same composition, we can't, I mean, if we should try doing a balance, we end up getting the same thing. So when it's a splitter, because it's the same composition, you can just get one equation. Because if I should do the 0.93 for each of them, I'll end up getting just one balance at the end of the day. So the balance I can get for this is N4 is equal to 100 plus N5. So if we should go ahead and then solve them, we'll be getting these values. So the values are there. I want you guys to try it out. Then if you come across any challenges, then you just let us know, right? And then we have another example here for the recycling, another example for the bypass. So you can try them out. The diagrams are here and then the answers are here. So you can try them out. If you should get stuck or you should get confused, just reach out to us and then we'll help you out with that. Is that okay? Okay.
So with this the material balance on the unit and the multi-unit, in the case where you have like mass fractions merged with mole fractions, you need to convert all of them to one form, either mole fraction, and then work with the mole fractions. You don't have to be working with mass fractions and mole fractions together. So if a stream composition is given based on mole percent and another stream is given based on mass percent, make sure you convert all of them to one form before you start solving.